Hello everyone, welcome to lecture 5 of the online course on modern display technologies, flat panel displays. Today's topic will be covering the overview of different flat panel display technologies which we could not cover in the previous lecture. So, here is the lecture overview. So, you can see that the three most popular technologies LCDs, LEDs and OLEDs were covered in the last lecture. Here we will look up to some latest technologies which are getting increasingly popular, okay, and there are a couple of technologies here which are very power economic. So, we will also be discussing those. So, first let us look into quantum dot displays. Quantum dot technology basically uses ultra small semiconductors which are a few nanometer wide. So, their purpose is to basically enhance the TV and monitor displays. So, this is the display and this is where the quantum dots are. So, these dots basically emit light when they are energized. So, they are not self emissive, you would require a backlight for them, okay. And depending on the size of the quantum dots, their emitted wavelengths basically vary. So, larger dots typically emit in the red and smaller dots emit in blue. And what you get as a result of quantum dot emission is that you get very pure, richer colors, you get deeper blacks and improved overall visual fidelity when you compare it against standard LED displays. So, these quantum dots, they are 0 dimensional, that means only a few atoms can fit into a particular quantum dot, okay, making them very ideal for precise color reproduction. So, you can understand the size they represent is very tiny. Now, Samsung's QN90B, that is a QLED TV, that means it is a quantum dot LED TV. So, you can now understand that this TV is basically using a combination of quantum dot technology as well as it is using mini LEDs for backlighting, okay, and the purpose is to reduce blooming and improve dark scene clarity. Now, what is blooming? Blooming in quantum dot LEDs or LED TVs is a visual artifact where light from bright objects bleed into surrounding dark areas that creates a halo effect. Now, the Samsung CHG90 gaming monitor leverages quantum dots for accurate colors and sharp visuals paired with 144 Hz refresh rate and widescreen, okay, or ultra wide screen. So, overall what we understood is that quantum dot technology can deliver much superior image quality. That is why they are very popular in high end TVs and gaming monitors. Next, we will look into reflective displays. So, reflective displays include electrophoretic displays that basically uses electric fields to move charged pigment particles within a suspension. So, that basically modulates the light reflection to create high contrast paper like images. So, reflective liquid crystal displays can also be used, okay. So, these basically consist of liquid crystal droplets which are dispersed in a polymer matrix, and here a dichroic dyes align with the liquid crystal that basically control the light absorption. So, that way also you can make reflective displays. The third type is interferometric modulator displays. So, you can understand from the name itself that this technology basically uses some sort of interference effect, okay. So, this technology is used in electronic visual displays that can create various colors via interference of reflected light. Next is electrowetting displays, where it basically this kind of displays use electric fields to manipulate the shape and position of the liquid droplets to modulate the transmission or reflection of the light that is falling on it. So, what are the key features? So, key features include, the most important thing is that these kind of displays do not require an internal light source. So, here is an example of reflective displays that you typically see in a car parking lot. So, it is basically an outdoor display because you need external light to fall on it to show the numbers. So, it does not have an internal light source. So, what are the advantages? Obviously, the light coming out of this is low. So, it will have very low eye strain, low power consumption, and it can produce excellent optical contrast, especially under high ambient light, and it is also suitable for portable reading devices and outdoor application as shown here. Now, power consumption and image retention. So, in this particular aspect, some refractive displays basically require the image being displayed to be constantly refreshed, okay, while some are bistable and they retain the image without any power. So, in bistable displays, energy is only consumed when there is a switching taking place. So, only the switching operation requires energy, and some have a video rate switching capability, okay, that means they switch really fast, while others are more suitable for displaying still images. Today, most monochrome reflective display technologies basically match the typical contrast ratio standard of 10:1, that is for the printed images that you see on a paper, but the reflectance of their bright states are still less than the typical value that you get out of a white paper, which is around 80%. Now, many color reflective displays rely on color filters, or you can use side by side pixel subdivision. However, to achieve color images with good brightness and saturation, multiple colors within the same pixel area is desirable. So, by fabricating a display on flexible substrate rather than using a rigid glass, so you can actually go for flexible displays. So, this can be made using this can be used for technologies including LCDs, OLEDs, and also electrophoretic effects, okay, and they can be fabricated with the advantage of being thin, robust, and lightweight. Next, what are the device parameters for different reflective display technologies? The important parameter that you will think of is the contrast and the reflectance. Most monochrome reflective displays achieve a 10:1 contrast ratio, as we discussed, but the problem is that their reflectance level is way lower than the white paper, which gives you around 80%. Next important parameter becomes power and speed. So, bistable displays, which are like electrophoretic or cholesteric LCDs. So, cholesteric liquid crystals, they are also known as chiral nematic liquid crystals. We will go into the details of this when you go deeper in the course, okay. They are basically a type of supramolecular assembly and a subclass of liquid crystal which are characterized by their chirality. So, when you have bistable displays like this, they use power only there is a switching happening, okay. While interferometric modulator and electroweighting displays, they basically support or they support the video frame rate. So, you can actually have much faster switching. Next aspect is flexibility. So, when you talk about electrophoretic, then polarizer free reflective LCDs and electroweighting displays, this can be built on flexible substrates such as the PET, and you can actually make flexible displays using this. So, now we move on to another technology which is called e-paper displays, which are like the electronic paper. You might have seen people using Microsoft Kindle or any other kind of similar devices for reading text or novels, okay, e-novels. So, this is where e-paper displays are coming into picture. So, what is the core technology here? The e-paper display basically mimics ink on paper offering high readability in sunlight and low power consumption. So, what is the technology here? Electrophoretic technology. So, it basically uses charged pigment particles which are suspended in fluid, and when you apply voltage, particles basically move to create visible text or images. So, we can actually see here. So, this is how it starts. So, the white ones are basically, so this is how e-paper display works. So, these are negatively charged pigments, these are positively charged pigments. So, when you change the electrode polarity, these pigments basically change position. So, this is kind of a microcapsule and this color is basically visible to the human eye. Okay. If you want a mixed pixel, so you can actually change the electrode polarity, accordingly the particles will basically appear. Okay. So, this is how the electronic ink basically works. It's basically made up of millions of tiny microcapsules, okay, inside which this kind of particles are basically changing position based on the kind of electrode potential that you are applying. So, this is the bottom electrode, this is the clear liquid which has got these particles suspended, and this is the top electrode through which the display is seen. Okay. So, what is the bistability here? So, once the image is formed, it remains there without a continuous power requirement. So, you require a power only when you want to switch the display. So, that makes e-paper highly energy efficient. What are the other advantages that you see here is that these are thin, lightweight, flexible, anti-glare, and they have wide viewing angles and also long battery life. So, this is typically what I was talking about, a Amazon Kindle which you can use for reading texts. Okay. So, these are typically used for e-readers, okay, and there are industrial IoT devices, then retail shelf levels and signage based on this technology. So, what are the benefits? The first thing is this thing is durable, customizable and scalable for large deployment in logistic and smart infrastructure. Also, the market outlook tells you that the growing adoption of this kind of technology across different industries due to sustainability, efficiency, and it gives a paper-like user experience. So, this technology has got a bright future going ahead. Now, we move on to something very cool, okay, or exciting I should say, head mounted displays which are mixing the real and augmented reality experiences to a viewer. Okay. So, the most FPDs have been developed to provide a format for direct view applications, like you directly go and view the images or the displays like TVs, computer monitors, laptop screens, tablets and smartphones. However, you will see that several FPD technologies including LCDs and OLEDs, they can readily be made into micro displays where the panel size is less than 1 inch, and you can have pixel sizes which are tens of microns or even smaller. So, such micro display, you can understand they are not good for direct viewing. You cannot see a display which is very tiny, lesser than 1 inch. Okay. So, they are not good for direct viewing. However, they have applications in emerging class of this head mounted displays. So, head mounted display system, what is the principle? It requires an optical system that basically directs light from this micro display to the viewer's eye. So, it basically involves a display system that is positioned close to the eyes, and then using an optical system, it can guide light from this miniaturized image source into user's eye. So, if you go back to the history where this actually initiated, the foundational concept of head mounted display traces back to 1830s when Sir Charles Wheatstone proposed the concept of stereoscope for viewing a pair of static photographs with slight disparities. Through over a century of technical development, the stereoscope has evolved into something called a new class of display technology that enables a new paradigm of applications. Okay? So, instead of static photographs and simple mirrors, today's head mounted displays are extremely advanced. They basically utilize diverse electronic display sources, cutting edge optical technologies, and advanced sensing, computing and communication systems that gives you additional functionality. And over many years of development, this head mounted technology, display technology has become a key enabler for virtual reality and augmented reality applications. So, here is a conceptual illustration of a monocular HMD system, okay, and this is how it looks like. So, what are the basic components per eye in a HMD? You will first require a modulated light source with drive electronics, that is basically your micro display that is doing the image delivery. Then you require some lenses, these are the optical viewer that basically guides the light emitted by this micro display to user's eye. Then you require some sort of optomechanical unit for housing this entire optics and securing this device to your head. Also, you require some sort of communication unit for data communication. Okay. However, this could be not required if you are doing a kind of wired connection to a computer unit where you are basically doing the image generation and data processing. So, a modern virtual reality and augmented reality head mounted display systems, they have some additional requirements, like they look for sensor suite for posture, gesture and environmental awareness. So, you get a look and feel of how the entire environment looks like, and accordingly your experience can be enhanced. Also, this communication unit becomes very important, where you can exchange data with remote sources, something like cloud servers or any nearby devices. The sensor suite that you see on the top, okay, what is the purpose of the sensor suite? This basically is a virtual coupling system to display content appropriate images. So, it basically responds to users location, head orientation and eye gaze direction. So, head tracker and eye tracker for motion is used, and also the gaze tracking is done. Also, the 3D depth sensors and built-in cameras, they basically create the depth map of the environment and capture images of the surroundings. So, the communication capability in this kind of system includes Wi-Fi, Bluetooth and even any other wireless module. Next important thing becomes the display modes. So, in a HMD there can be different display modes like monocular HMD. So, this basically monocular means it uses a single micro display and optical viewer. So, it is basically catering to only one eye. So, this is basically used for displaying the image to one eye, something like Google Glass. Okay. Now, you have biocular HMD. So, you have two identical optical assembly, one per eye, and they basically display the same image to both eyes. And you then have another type which is called binocular HMD. So, here also you have two optical assemblies, but they display slightly different images to each eye for stereoscopic or 3D viewing. So, this is where you get the 3D aspect. Now, let us look into the different categories of head mounted display. So, you can categorize head mounted display based on their based on their visual experience. So, one category is called immersive displays. So, immersive displays basically block the user's view of the real world completely, like this. So, you can't see what is happening in front of your eyes. So, you are basically looking into fully the computer generated virtual environment. So, these some examples are like Oculus products. So, here you have optical viewer which are placed directly in front of eyes. The second category is called see-through displays. So, see-through means you are actually able to see the real world and it blends the real and the virtual scenes. Okay. So, here also there are two types, one is video see-through. So, that blocks direct view of the real world, but rather uses camera to capture the real world thing and then digitally blend the real world and the virtual images. So, here the performance basically depends on the camera quality, its resolution and latency. However, it is easier to handle the mutual occlusion between the virtual and the physical objects, because both are now in the virtual domain. The other one is called optical see-through, right. This is what I was talking about, that you can directly see. So, here it uses an optical combiner to overlay the virtual images onto the direct view of the real world. So, in this case you are not dependent on the camera resolution or latency, you can directly see it. So, it maintains the full real world resolution. So, there is no compromise on resolution. It is less intrusive and it is ideal for hand-eye coordination tasks, because you are seeing the real world directly. So, it is preferred for applications where an unobstructed real world view is essential. So, what are the different emerging technologies in head mounted displays? Eye tracking for user interaction and focus adjustment, addressable focus cues to simulate natural vision depth, occlusion capability to enhance AR realism, high dynamic range for improved image quality, light field rendering for realistic 3D viewing. Please note that a lightweight, non-intrusive and comfortable HMT is crucial, yet it is very challenging to develop for effective AR VR experiences. So, finally, we will look into touch panels also, which are not directly display technology, but they also play a very important role, because this is where the human senses and the machine interact. So, humans interact with the world through 5 senses, we all know: sight, hearing, taste, smell and touch, and display basically stimulate human vision. So, that is one of the most dominant sense. So, other machines like TVs, phones, laptops, their output images that will basically trigger your sight, and also another important output is sound that will trigger your hearing. Now, people need to think of what are the input devices in human machine communication. So, the input devices that basically allows humans to communicate with the machine, first one is the remote control for TV that all of us uses, the keyboard and the mouse for the computers, and typically for phone, tablet and car systems it is touch panel. So, touch panels are typically placed over the displays and they must be optically transparent. So, how they work? They basically work based on detecting touch by some change in electrical parameters like resistance or capacitance. So, let us look into a resistive touch panel. Okay. So, the touch functionality it can detect is single touch, that you have seen applications such as in ATM machine, okay, or you can also think of multi-touch, which requires controlling the device with multiple touches like pinch, zoom or something like that, or scrolling, okay, that you use in smartphone and tablets. So, there are different types of touch panels. The first one is resistive touch panel. So, here is the structure of the resistive touch panel. So, there are basically two substrates, one at the bottom, one on the top. Okay. So, they both have transparent resistive layers, okay, which are basically transparent conductors separated by air gap, okay, and you can see the outer substrate is basically deformable. So, how it works? There are some dot spacer which basically maintains this gap. Now, the touch basically causes the contact between the upper and the bottom conductor. So, here there is some gap, but as soon as you touch it, okay, you apply some pressure here, these two levels will basically touch, and the contact position will basically change the resistance, which is read out by some driving circuitry. Now, what is the limitation in this case? You can understand that low optical transmittance is there because of this air gap, because you want your display to give out all the light together. So, but here it basically reduces the illuminance. Next is the capacitive type. So, here how it works, a conductive object, something like a finger, when it basically acts as a capacitor connected to the ground, right. It basically alters the measured capacitance. So, there are two types of measurement. One is self capacitance measurement, one is called mutual capacitance measurement. So, self capacitance, it basically measures at individual electrode. When you have mutual capacitance, you basically measure the capacitance between a pair of electrodes. So, what is the requirement here? A conductive object such as a finger is needed to activate the touch functionality on the capacitive touch panel. That is why you might see that when in winter, when you put winter gloves and try to touch your cell phone, it is not working. It only works with your finger. So, it requires a conductive, or you can say capacitive or conductive object, okay, to work. So, there are two configurations. One is called outcell touch panels. So, here the touch panel is basically stacked physically on top of the display, and but it is easy to think of, but it adds to the module thickness and complexity. Then there is something called on cell touch panel. So, here the touch panel is fabricated onto the outer glass substrate of the display itself. So, you do not need to have double outer layer. So, it basically reduces the module thickness. There is another one called in cell touch panel. So, it is basically integrated inside the display. So, it basically uses the bottom substrate of the TFT panel, thin film transistor panel, that is used to trigger your display, but it requires a suitable layout and driving scheme. So, this basically simplifies the fabrication and reduces the overall thickness further. So, what are the use cases of different touch panels? So, we understood that resistive touch panel, they are suited for diverse input methods, but they provide lower illuminance. Capacitive touch panels, they are popular for finger touch interfaces, something like smartphone, okay, but you need to remember that you require a conductive input, right. And the integration, when you consider on cell or in cell, they are basically focusing mainly towards thinner streamlined design, so that the overall device thickness becomes thin and it should be lightweight and flexible. So, with that we conclude this lecture. If you have got any query, drop an email to this email address mentioning the course name on the subject line. Thank you.